dear friends. So in the previous video lecture, we started talking about cutting plane algorithms. In order to solve integer linear programming formulations, we initially considered the branch and bound algorithm. And the next algorithm that we started to learn was the cutting plane algorithm. In the previous lecture, we talked what exactly a cutting plane algorithm, how it works. If you remember, we said that like the branch and bound algorithm, cutting plane algorithms also starts with the LP relaxation of the problem. It solves the LP relaxation. If the result is integer, then that's optimal. We stop it. Otherwise, if it's not integer, then we look at the optimal simplex tableau, okay, and we generate a cut from this. So a cut means an artificial constraint, an additional constraint that we add to our model. Okay, but this artificial constraint is a spatial constraint. It is not a regular constraint. It has basically two properties, so that we call it a cut. The first property is when we include this constraint to the model, the initial relaxed optimal solution should not be feasible anymore. Okay, so it should be out of the feasible region. And secondly, again, after inclusion of this constraint to the model, all integer feasible solutions on the original model should still remain feasible. We shouldn't cut any one of the integer feasible solutions. Okay, so therefore, a constraint, an artificial constraint, to be a cut, it needs to satisfy these two conditions. Okay, so we start with LP relaxation. If it is not integer, we find such a constraint, include it into the model, and we solve it again and look at the solution, look at the optimum solution. But when we include this constraint and solve the model again, it's still a linear program. It is not integer, still a linear program. So we still use the simplex algorithm to solve it, and then look at the solution. If it is integer, stop, it's optimal. Otherwise, find another constraint, include in the model, and continue repeatedly in this way until you come up with an integer solution. Okay? This is how, in general, the cutting plane algorithms work. On the other hand, we learned how to generate such spatial cuts with the procedure developed by Gomory. That's why this procedure or these cuts are called Gomory cuts, or sometimes they are called fractional cuts, because we are interested in the fractional parts of the coefficients of variables in the objective function or in the constraints. Okay, so now assume that we learned how to generate those Gomory cuts. What is next? How shall we find the new optimum solution? One method, of course, is to do this. You have your original model, you relax the variables, and you solve it using the simplex algorithm, right? And by simplex algorithm, you can solve it. If the solution is not integer, generate the cut, include it to the model. So you have now a new model with an additional constraint. What you can do is you can start from the beginning and solve it again. But the thing is, we already solved that problem and we have this optimal tableau. Okay, we already have that tableau. Why shall we start from the beginning? Is there a way to start from that optimal solution and then find the new solution from this one? And the answer is yes, we can do this, and by doing this, we will make our algorithm faster. It will find the solution quicker, because you see, in the previous case, the optimum solution of the LP relaxation, when we include a cut, most probably the new optimum solution to the new problem with the inclusion of this cut will be in the neighborhood of this one. So if you start from the beginning, maybe you'll start from an extreme point which is far away, and by jumping through other extreme points you will reach to this one. But if you start from this old optimum solution, then you can find this new solution maybe in an easier or shorter way. So we will learn how to do this And the algorithm that we will learn is the dual simplex method. Okay, so let's get started. If you remember last time we made this example, and this is the optimal simplex tableau. Okay, when we solve the given problem, the LP relaxation of the given problem, this is the optimal simplex tableau, and you can see that x1 is 4.5, x2 is 3.5, and z value optimal LP relaxation is 66.5. And this is not an integer solution. It means that according to the cutting plane algorithm, we need to include a new cut. And how did we generate these cuts? Remember, for each row, either from row 0 or the row corresponding to this first constraint and the row corresponding to this second constraint, we can generate cuts if the right-hand sides are fractional. By the way, if you remember when we learned the simplex algorithm in the previous course, we write another column here for z, okay, and for that column we have 1 in row 0 and zeros in all others. So different books may have different formats, but basic idea is the same. So instead of including this column in every case, because it never changes, it's always 1 0 0, you don't need to repeat it in all tables. You just ignore it, but you know that that column is there. Okay, so in this book they don't include this row, this column. Okay, so from each one of these rows now we can generate a cut, and the optimum solution to this one is this. And let's remember how do we generate these cuts? What is the procedure? The procedure is easy. We represent each coefficient. So the coefficient of the constraints are these numbers here. This is the coefficient of x1, this is coefficient of x2 and x3 and x4, and this is the right hand side. So for each one of these coefficients, we represent them as an integer plus a positive fraction. This is important. Integer plus non-negative fraction. Okay? This second part is important, non-negative fraction. And we learned it how to do it last time. So if you look, this is integer. So basically, we can just eliminate it. And this is also integer. We can eliminate it. For z, we have 1 here, if you remember, and we can eliminate that one also. So this is not an integer value, 63 divided by 22. So it is something 2 point something. So it means that 2.19 over 22, I guess. So what we can do, we can ignore the integer part, which is 2, and just keep the fractional part. The fraction means it's a number between 0 and 1. The fraction cannot be larger than 1. So this 63 over 22 is not a fraction. Okay, so we should first take out all the integers inside this number, and the remaining fractional part, which is less than 1, is our fractional part. Okay. Similarly, if you look at this, it is 1 plus 9 over 22, so we can ignore that integer 1 and we will have 9 over 22 here. And again, on the right hand side, the integer part is 66 and the fraction is 1/2. So by doing this, we need to change the equation sign in this constraint to greater than or equal to. Okay, so this is how we generate the cuts. Okay, now let's consider that optimal tableau, and from that optimal tableau, by looking at the x2 row, which is this row here, okay, we can write our cut as minus 7 over 22 x3 minus 1 over 22 x4 plus 1 over 2 less than or equal to 0. Remember last time I told you that in our procedure we write the cuts so that originally for this constraint we have this 7 over 22 x3 minus plus 1 over 22 x4 greater than or equal to 1 over 2. So this is the original cut after the procedure. But I told you that for the sake of further finding the new optimum solution, the rest of the algorithm, we want this inequality to be less than or equal to. That's why we multiply this constraint by -1. And then if you move this 1 over 2 to the left hand side of the constraint, you can represent the cut in this way, or you can keep this on the right hand side as -1 over 2. Okay, now this is the cut. But remember, in Simplex Tableau, we always have equations. What do we do with this cut? We will include this cut in our Tableau, Simplex Tableau. We will add it to our Simplex Tableau. Okay, how do we do it? As I said, we move all the constant terms to the right hand side of the constraint, but in the Simplex Tableau, the sign must always be equality. But in this cut, we have less than or equal to. And how do we convert a less than or equal to constraint into its standard form with equality? Remember our previous course, OR1 course, we do this with by including a slack variable. Okay, so we add a slack variable to the left hand side and make it equal to -1 over 2, and this slack variable is a greater than or equal to variable. This is a new variable. So what does it mean? Including a new constraint to the Simplex Tableau, optimal Simplex Tableau, requires one additional row. You see, initially we have these 3 rows, and now I have included a new row and one additional column because I added a new variable to the problem. Okay, this is the slack problem. Okay, then what are the values in the Tableau for this new row and new column? Okay, for the new column S1, this is a variable which only appears in this constraint. So in all other constraints and in the objective function, it doesn't appear. So for all others, we put a 0, and for this constraint, we put a 1 here. And this is one reason, this is the reason that we converted this constraint to less than or equal to, because we want this sign of this variable to be +1. Okay, if it is not +1, if we keep the original version here, we should subtract -s1, we should write -s1. And when we put it into our model, we should write it -1 here. But what's the problem with a -1 here? Remember, in Simplex, we always need this canonical form. Canonical form is the identity matrix. So we need to have variables with a 1 in only one of the constraints and zeros in all others. So for the first constraint, we have 1, 0, 0. For the second, we have 0, 1, 0. And if we have this as a 1, we have 0, 0, 1. But if it is -1, then we don't have the canonical form. So in order to have the canonical form, we converted this cut to a less than or equal to, and we included a plus slack variable here so that we have the canonical form. Okay, so this is the column of the new variable. What about the row of this constraint? So basically, we write the coefficients. Okay, so for x1, 0. There is no x1 here. There is no x2 again. The coefficient is 0. x2 we have -7 over 22. x4 we have -1 over 22. s1 is 1. And the right hand side is -1 over 2. Okay, so now this is the modified optimum tableau. Okay, what to do next? Is this the optimum tableau? And if you remember, this was a maximization problem. Okay, in a maximization problem, a tableau is optimum if all the coefficients in row 0 are non-negative. And when you consider that, Yes, all of them are non-negative, so this should be an optimal solution. But be careful. There is one more restriction. In regular simplex method, we always work with feasible problems. We start from an initial feasible solution, then from that one we move to a new feasible solution. Okay, but now here we included a new constraint, and this new constraint, what did it do? Is it still feasible? We need to check it. And how do we understand if a Tableau, simplex Tableau is feasible or not? Basically, you should look at the right hand side of the constraints. Remember, a Tableau is feasible if all right hand side values are greater than or equal to 0, non-negative. But you see, for this new constraint, we have negative, -1/2. It means that this Tableau is not feasible. So if a Tableau is not feasible, you cannot say that it's optimal. Okay? First of all, it should be feasible, and this Tableau is not feasible. And this, be very careful, this is a point of understanding. We said that a new constraint is a cut if it eliminates the previous optimum solution for the LP relaxation, right? So look, we included a new constraint, and now with this new constraint, the old solution, which is this one, the old solution is infeasible now. It's not feasible because the right hand side is negative. So what does it do? It eliminates the previous solution. So can you understand it? By adding this constraint, by having a negative right hand side here, we satisfy that this solution is not feasible anymore, and we satisfy one of the conditions of a cut. Now what shall we do? How shall we find a feasible solution from this Tableau? And the thing is, now you cannot use regular simplex algorithms because it always works with feasible tableaus, but now we have an infeasible Tableau. It means that we need a new method. Let's see what's it. Okay, so the procedure that we are going to learn to convert the Tableau to a feasible solution is, in fact, this similar, a familiar procedure, which is called the dual simplex algorithm. Okay, so it is very similar to the simplex algorithm, but it's not regular simplex algorithm. It's the dual simplex algorithm. It consists of 3 steps. First, I will show you the steps and we will make examples. And if you remember the regular simplex algorithm, understanding and learning the dual simplex algorithm is very easy for you. The name is dual simplex algorithm because you will see we will be making some opposite things with respect to the simplex algorithm, but still the steps are similar, as I said. In regular simplex, remember, when we have an initial simplex Tableau, the steps were like this. You first decide on the entering variable. An entering variable depends on, of course, whether it's a maximization or a minimization problem. If it's a maximization problem, entering variable is the variable with the most negative coefficient in row 0. If all coefficients in row 0 are non-negative, then you found the optimal solution. Okay, you select the most negative one as the entering variable. Then the second step is to find the leaving variable, and for leaving or exiting variable, you make the ratio test. And the ratio test is basically the right hand side value divided by the pivot column, the coefficient of the variable in the pivot column. But this is done for all positive coefficients in the pivot column. Okay, and then you select the variable with the minimum ratio as the leaving variable. Then you make elementary row operations to find the new tableau. Okay, so this is the steps of the simplex algorithm. Now let's consider the dual simplex algorithm and let's identify the differences. The first step is, okay, we are going to give this algorithm for a maximization problem. If the problem is not minimization, remember, is not maximization. Remember, if it is minimization, what we can do is we can multiply this by -1 so that the problem becomes maximization, right? So the maximization is in fact the negative of minimization. So just multiply row 0 by -1 and you will obtain a maximization problem. Okay, so reformulate the problem as a maximization. And in row 0, all values should be non-negative now. Okay, so row 0 coefficients should be non-negative. And the right-hand side values, there should be at least one non-positive value. Otherwise, it means that the tableau is already optimal. Okay. In step 2, what do we do? In dual simplex, in regular simplex, we first decide on entering variable, then leaving variable. But here, we first find the leaving variable, then decide on the exiting variable with a ratio test. Okay, so the leaving variable is decided by looking at the right-hand side values, not row 0, but to the right-hand side, and select the variable which with the most negative right-hand side value as the leaving variable. And this, the row of this one will be your pivot row. Okay, so if let's say this is your tableau, okay, you have row 0 here, one constraint here, another constraint here. Then you look at the right hand side and let's say that this right hand side value is the most negative, so you decide this to be your leaving variable. Then this row becomes your pivot row. Okay. So then we compute the ratio for each non-basic variable that has a negative coefficient in the pivot row. Okay, now we need to calculate the ratios. And the ratios are calculated by the row 0 coefficient divided by the coefficient in the pivot row. Row 0 divided by this. So we may have, let's say, variable x1 here. We may have variable x2 here. And we may have variable x3 and etc. Okay, so we take the ratio of x1 in row 0 divided by in this pivot row, but only if this is negative. For example, if this value here is positive, we don't use it in, we don't consider it in the ratio test. Okay, again, if this is negative, then we take the ratio of x3 in row 0 to this value. Okay, basically the ratio is coefficient of the non-basic variable in row 0, of course it should be non-basic, to the coefficient of that non-basic variable in the pivot row. And then which one should we select? Again, we select the smallest ratio. Okay, but remember, in regular simplex the ratio test was found like this: right hand side divided by the pivot column, right hand side divided by the pivot column. In this way, we do the opposite and we find the row 0 divided by pivot row, row 0 divided by pivot row. Okay, but we do the same thing. The selection is the same because we select the smallest ratio as the entering variable. Okay, but this smallest ratio is in terms of absolute values. Be careful. Why we are saying absolute values? Again, because row 0 coefficients are all positive. And we find the ratio for only negative coefficients in the pivot row. So positive divided by negative, the result will be negative. But while comparing two ratios, ratio of x1 to ratio of x2, we take their absolute values, okay, and compare them with these absolute values, not the negative numbers. And we select this as the entering variable. Okay, what did we do until now? We decided on the leaving variable, we make a ratio test and decided on the entering variable. And then the new tableau is found by elementary row operations, again the same way in the regular simplex, because with this ratio test we decided on the, let's say, entering variable as, let's say, x1, x3, and it means that now this element here is the pivot element and we want this column to have 0, 1, 0. In order to satisfy that, we make elementary row operations. So this is step 2. Okay, in step 3 of the algorithm, we check the new tableau. If in the new tableau, if there is a constraint with negative right-hand side, it means that this new tableau is not feasible. So we should select this one as the entering variable. Then we will make a ratio test. And while doing this ratio test, in the pivot row, assume that all entries are not negative, non-negative. They are either 0 or greater than 0. So what is the conclusion? The conclusion is there is a leaving variable, but we cannot make ratio test. So the tableau or this new tableau or this problem is infeasible. There is no solution to this problem, so we stop. Otherwise, if the right-hand side of all each constraint is non-negative, it means that you found a feasible solution. And in the row 0, we know that all of them are non-negative again. It means that you found an optimal solution. So stop. As soon as you find the solution in which all right-hand sides are non-negative in dual simplex, we stop because we found the optimum solution. Otherwise, what's otherwise? If there's at least one right-hand side which is negative, and in this pivot row, there's at least one non-basic variable with a negative coefficient, then we can make this ratio test. So it is not infeasible, it is not optimal. We need to make one more iteration by selecting this as the leaving variable and deciding on the entering variable and make new elementary row operations and find the new tableau. Okay, so these are the steps of the dual simplex algorithm. As I said, if you remember the regular simplex algorithm, the steps are similar, but in a different way. Instead of deciding entering first and leaving next, we now decide first leaving, then entering. And the ratio test is a little bit changed. Okay? So let's make some examples and try to understand better. So this is the optimal tableau after we included this new constraint to the model and this new variable. And we said that this is infeasible. This tableau is infeasible. I am not saying that the problem is infeasible. I am saying that this solution is infeasible. Okay, this solution is infeasible because the right-hand side is -1/2. Then let's apply this dual simplex algorithm to try to obtain a feasible solution. Okay, the first step, this is already a maximization problem. Okay, all row 0 values are non-negative. That's okay. And we have at least one non-positive or negative right-hand side value. Okay. So in step 2, what do? We decide on the leaving variable. And the leaving variable is the one with the most negative right-hand side. There is only one variable with a negative right-hand side. So we decide on this to be leaving. So what is the variable that is leaving? The basic variable corresponding to this row. It's written here. Okay. So S1 is leaving. S1 is the leaving variable. Now we need to we need to find the entering variable. and the pivot row is this one now. Okay, and we need to consider the non-basic variables. You should be able to identify which variables are basic and which are non-basic. So here x3 is non-basic, right? And x4 is non-basic because x1, x2 and s1 appear in the canonical form. They construct the identity matrix. Okay, now it means that we need to consider x3 and x4 for the ratio test. Both of them has a negative coefficient in the pivot row. So it means that I will calculate the ratio for both of them. Let's first calculate the ratio for x3 first. Okay, the row 0 coefficient is 63 divided by 22, right? This is row 0, and this will be divided by the coefficient in the pivot row, which is minus 7 over 22. Okay, but we should take the absolute value of this one, and when you do, these 22's cancel out, and 63 divided by 7, this makes 9. Okay, so this is the ratio for x3. What about the ratio for x4, the second non-basic variable? Again, row 0 coefficient is 31 divided by 22. And pivot row coefficient is minus 1 over 22. And again, we need to take the absolute value. And these 22's cancel out. And the result is 31. Okay, so the ratios of x3 and x4. And the algorithm says that select the one, the smallest one as the entering variable, which is this one. So it means that x3 enters. Now x3 is the entering variable, s1 is the leaving variable, and this is our pivot column. And what do we want to do? We want to replace this s1 with x3 in the basis. So S1 has 0, 0, 0, 1. It means that for x3, I need to have 0, 0, 0, 1 here. Okay. By making elementary row operations, I need to convert this to 0, 0, 0, 0, and 1. Okay. So for this purpose, what do? I need to make this value equal to 1. It means that I need to multiply this row by minus 22 over 7. And if I do it, this will become equal to 1. Then, in order to make this value 0, I need to multiply this. Let's say you can do either this original constraint, or you can consider the new constraint after multiplying by this one. If you consider the original constraint, in order to make this value equal to 0, you need to multiply this original constraint by 1 over 7, minus 1 over 7, and add it to here, so that this will become 0. And the other values in this row will change accordingly. And then you will do the same thing for this row, and you will do the same thing for this row in order to make these values 0. And after these elementary row operations, I'm not going in detail, but please take your pen and pencil and refresh those elementary row operations to understand it. Okay. After we do all these elementary row operations, we got this next solution. So after the elementary row operations, we got this tableau. Now we need to look at this tableau. Is it feasible? If you look at the right hand side values, all of them are positive. It is feasible. It means that dual simplex is completed, and we found the optimum solution for that problem. But remember, what are we trying to solve? We are trying to solve an integer problem. We solved the LP relaxation and it was not feasible. The LP relaxation didn't give us an integer solution. Then we added a cut, which is this last constraint here. We added a cut to the model, and then we re-optimized, and this is the solution of that re-optimization. But the thing is, this is still not an integer solution. It means that we couldn't find the integer solution, and we need to continue with the cutting plane algorithm. What shall we do? We need to include a new cut. Okay, then let's include that cut. Let's write a cut corresponding to this row. But if you look at this row, you will see that the coefficient of z, which is 1, it is integer. Coefficient of x1 integer, x2 integer, x3, x4, s1, and the right hand side, all of them are integers. And what do you obtain as a cut here? Nothing. Okay, no cuts corresponding to this row. X2 is already integer. X2 is equal to 3, the right hand side. So if you do the same thing for the row 0, again you will not be able to obtain a cut from here. So we should consider these two rows for including a cut, for writing a cut. Okay, you can use any one of them. Let's use this x1 row. Try to write a cut. The first thing is to write every coefficient as an integer plus a positive fraction. There is the z coefficient here is 0. So it's integer, eliminated. x1 integer, eliminate. x2 integer, eliminate. x3 integer, eliminate. So x4 is integer 0 plus 1 over 7. Okay. So we can write this x4 as an integer plus a fraction like this, and this 0 eliminated. S1 minus 1 over 7. Be careful. You cannot just say that, okay, this is fractional and we continue with it. No, because it's negative. It should be positive. So we should be able to write this an integer plus a positive fraction. Integer can be negative. So basically you can write it like this. Minus 1. Okay, plus 6 over 7. And if you write this, you obtain as a result minus 1 over 7. Okay, so this minus 1 over 7 here is equal to minus 1 plus 6 over 7. And what do? We eliminate the integer part, and the remaining part is 6 over 7. And for the right hand side, we have the integer part as 4 eliminated, and the remaining part is 4 over 7. And what do? Don't forget, we replace the sign with greater than or equal to. And then in order to convert this greater than or equal to less than or equal to, you multiply it by minus 1 so that we can include it in the Simplex Tableau. Otherwise, if you don't want to include it in the Simplex Tableau but just want to write the cut, you can keep as it is greater than or equal to 0. Okay, so this is how we did it. Integer parts are removed, and this equality is converted to greater than or equal to, and then we represent it as less than or equal to. And in order to include this into our optimal tableau, we include now a new slack variable to convert the sign to equality, and this slack variable is now s2. The previous slack variable that we included in the previous iteration is still in the problem, and this is a new variable. And also, when we add this to our optimal tableau, you see originally in this problem we had only 2 constraints. In the previous step we included one more constraint, and in this step we are including a new constraint. So at each step the number of constraints increases, and the tableau expands by adding one row for a cut and one coefficient, one slack variable. Okay, so now we need to re-optimize this. You see the right hand side is negative. It means that this tableau is not optimal anymore. So we need to make dual simplex iterations. First thing is to decide on the leaving variable, and leaving variable is the variable with the most negative right hand side, which is this one. which corresponds to S2. So this is our pivot row now, pivot row, and then we need to identify the entering variable, and for that we need to make the ratio test, and the ratio test is the non-basic variable. X4 is a non-basic variable. Row 0 coefficient is 1. I'm writing here 1 divided by minus 1 over 7 in absolute value, and you obtain 7. And the other non-basic variable is S1, and for that we have 9 row 0 coefficient divided by minus 6 over 7, okay, in absolute value, and this is 63 divided by 6, and the smallest of these is 7, so it means that X4 enters. So this is our pivot column, and we want to convert this to 0, 0, 0, 0, and 1, and for this purpose we will make elementary row operations. Okay, make those please by yourself, and we will reach the next tableau. So after adding this second cut and making this dual simplex iteration, after making this elementary row operations, we see that all right-hand side values are positive. It means that we found the optimum solution for the LP relaxation. And what is that solution? Let's see. X1 is equal to 4. X2 is equal to 3. So remember, in our original model, we have only X1 and X2. This X3 and X4 were the slack variables. And when you see the original variables, which are integer restricted, X3 and X4 are not integer restricted. They are greater than or equal to 0, continuous variables. You don't need to look at their right-hand sides. Only X1 and X2, original model variables. They are integers. And what does it say? We found an integer solution for the LP relaxation with the included cuts. And this integer solution is the optimum solution for our original model. Okay, so we found the optimum solution for integer for our original model by first solving its LP relaxation, then including one cut and solving again, and including the second cut and solving again, we obtain the integer solution. This is how cutting plane algorithms work. Okay, now this is an example for you. During the cutting plane algorithm, remember, after including the first cut, okay, and resolving it, we obtain this solution. Okay, and this solution still was not integer, and we decided to select this row and include the cut. Now, what you could do is you could select this row and write the cut corresponding to this row and re-optimize. Now, your task is to do it by yourself. Please write the cut corresponding to this row, okay, include it in the Tableau, then follow the steps of the dual simplex algorithm. Find the leaving variable, make the ratio test, find the entering variable, make elementary row operations, and re-optimize, and try to find the optimum solution. And basically, you should be able to find the same optimum solution with the previous one. Okay, so please try it by yourself. And this is the solution if you consider that row. Okay, we have this constraint. Now, how shall we write the cut corresponding to this one? We will first write each coefficient with an integer plus a fraction. So x3 is already integer. You cannot have a fractional part. If you like, you can write 1 plus 0 x3. Fractional part is 0. Okay, and this is 0 plus 1 over 7 x4. Then for this S1, you have minus 4 plus 6 over 7. This fractional part is very important. It should be plus. And for the right hand side, we have 1 plus 4 over 7. And then just ignore the integer parts, this part, this part, this, and this, and convert this to greater than or equal to 0. And then multiply all of them by -1, and the cut that we obtain from this constraint is this. Now you should include this one into the previous Tableau and make the dual simplex iterations. But the thing is, if you look at it carefully, this is the same cut that we obtained by using the previous row. Okay, exactly the same cut. It means that all the steps of the dual simplex algorithm will be the same. So you will find exactly the same solution. Okay, so this is the end of the cutting plane algorithm, our discussion on cutting plane algorithm, as well as this is the end of our discussion on integer programming algorithms.